All right, well, why don't we kick this off? I know it's one last seminar before now and your spring break. So let's of course, thank you very much for attending today. It's right before spring break, so thank you for staying here to listen to the talk. Professor Lee also appreciate it. Today we really are honored to bring our guest from Michigan State University, Professor Zhaojian Lee, who is a Restsetter Distinguished Associate Professor. That's some combination that you don't find a lot. Distinguished and Associate Professor, which means how impressive he is at such a young age. He's already a distinguished professor. He's affiliated with the Department of Mechanical Engineering over there. He got his master and PhD degree both from aerospace engineering from University of Michigan. He has been working there for a couple of years. And actually, before he joined Michigan State University, he worked for General Motors for a year. So he also had that kind of industry experience. He is actually senior member, NSF Career Awardee, and many other awards, and associate editor for several journals, and published like more than 80 papers and a few patents. I think this talk is very interesting to many of you today, especially now we're talking about physical AI and stuff like that. So without further ado, let's welcome Professor Lee.
Yeah, thank you very much, Jian, for the kind introduction. Yeah, so this work actually, when I first joined Michigan State, right? So my training background is more controls and learning. So when I first joined MSU, and the robotics research is kind of reviving. So I said that I want to do some robotics, and I was looking for applications, right? Robotics typically is tied to applications. So then I looked around, I found that actually agriculture is a strength for MSU. So I look at the ag robotic research, and among those, I found this apple picking robot quite interesting and also economically impactful. So I have then down the road worked on this project for more than 5 years now. So it's been a very fun journey for me. So today I'm very honored here to share some of my research on this topic. So just some background. So apple is one of the most consumed fruits in the US and across the world. And also it's very economically impactful. So each year US produces around 11 billion pounds of apples, which contributes to more than 3 billion value just at the farm gate, right? And in the fresh market, it will be much more than that. And unlike the major crops that have been fully mechanized for harvesting, right? This is a picture to show how the majority of apples are harvested today. You can see that the workers have to climb up and down the ladders, carry a big heavy bag, and after the bag is full, then dump it into the bin. So it's a very labor intensive. And also the industry is actually facing a big challenge because of the labor issues. As you can see, at least here, the annual labor for just harvesting, right, needs more than 15 million work hours. And the harvesting labor accounts for more than 15% of their total production cost. Just to give you some numbers. So in orchards in Washington, right, Washington state produces more than 65% of the fruits, so the major production state. So in Washington state, their hourly rate for the seasonal labor, right, so it's heavily relies on the seasonal labor H-2A program, is more than $35 per hour, which is a great burden for the growers. So that's why they need some help from the automation, from robotics, right? As you can see from the news, that the growers are facing a lot of management challenges for the harvesting labor and also the cost, right? They're growing so fast. So as a result of that, right, there are a lot of efforts have taken to address the labor challenges, right? So we are talking about automation and harvesters. So there are two major categories of harvesters. So one is this shake and catch harvesters. So the idea is to have a device that can shake the trees, and so that the apples will fall down and then it can catch the fruits. So this is a very efficient way to basically detach the fruits from the tree. But there are big issues with this harvester. First of all, it causes big damages to the tree, and it can only work for relatively older trees. Okay, and also another important factor why this is not adopted widely is it will cause a lot of bruising for the fruits, right? So there's a big economic gap between fresh market fruits versus the processing fruits. So if the fruits go to the processing, then the value decreases significantly. So that's why the shake and catch harvester is not widely adopted, right? Very rare usage for those kind of harvesters. And then the second class of harvester is we call this fruit by fruit harvester. And over the past 2 decades, there are a lot of work on this fruit by fruit harvester. However, right, due to the various reasons, first of all, the technical challenges, but also there are some traps the research typically falls in, make the system too complicated, too costly, and also not designed for the real ultra conditions. And as a result of that, so far still, there's no commercial robotic system to harvest apples. So let me talk about the key objectives and challenges for a fruit by fruit apple picking system. So we have been working with growers across Michigan, Pennsylvania, and Washington extensively to understand their needs, right? And their kind of requirements to design a robotic system. So I'm listing a few major kind of metrics for the success to develop a robotic system. So the first one is the throughput or the efficiency, right? So we're talking about this module, right? Two-arm module. The two-arm module should be comparable to one human picking labor, right? Which can pick the fruits at 2 to 3 seconds per fruit. But considering the transit time, if the module can pick a fruit at 3 seconds per apple, actually the growers will be quite happy about that. And also the picking rate. The picking rate is that, let's say if you have one tree that has 1,000 apples, right? After the robot passed through, how many of the fruits will be successfully picked? So that's what we call picking rate. And then also bruising rate, right? Bruising rate means after among the picked fruits, how many fruits will be able to go to fresh market versus it has to go through processing. So the less than 3% bruising rate, that's basically comparable to human pickers. So human pickers also cause bruisings. And so those are like the design objectives for us to keep in mind when we iterate the system. And then I'm going to talk about some of the challenges. Why so many failures over the past 2 decades, right? So the first one is actually when you think about the apple picking, right? You will probably initial thoughts were if you never went to orchard to observe the orchard condition, you will think that apples are just hand there and then you can pick it's really quickly. But in reality, right, this is some pictures from the real orchards, commercial orchards. As you can see that there are a lot of occlusions by foliage and all by branches. And in the real orchard environment, you have to face with the various lighting conditions. So you have direct sunlight and you have backlighting, means that the scene is quite dark. Okay, and also the apples are different in variety, size, and color. You need to be able to deal with those things. And also on top of that, right, meeting the requirements, which are kind of challenging to meet in design. So here's our journey. We actually started with a very simple proof of concept, right? This is the 2020 version. We just quickly went to the orchard to test the vacuum-based picking, whether this is a feasible solution. And of course, we have some automation to kind of approach the fruit. This is where we start. And over the years, yeah, we have made steady progress. So we refine our hardware, software, and also go from one arm to multiple arm. And this year, I will show that we're actually going to mount 4 of the 2-arm modules and to have 8 arms to have a complete system. But yeah, and I'd like to acknowledge the sponsorship from the USDA and the National Science Foundation. So we got a $3.5 million USDA project for automated harvesting and also infused sorting, which I'll also touch on that. So now let me give you a very quick overview of the overall system, hardware and software. Then I will talk a bit more about some more scientifically interesting aspects of this project. So here is the hardware overview, right? So we have something we call a sunscreen system. Basically, try to physically mitigate the effect of the different challenging lighting conditions. And then we have a key robotic module, 2-arm robotic module. And then we also have a fruit handling system, right? After we pick the fruit, we need to transport the fruit to the bin, right, without damaging the fruit. So those are the key modules. And then within this core robotic harvesting module, so we have a perception system, right? Perception system consists of the 3D cameras, and then we have a relatively simple and effective design. So we built the robot from scratch, right? We are not using the off-the-shelf robotic arm. We built the system in a way that it's simple but effective, good enough to pick the fruits. And then we have a vacuum system to harvest the fruit. This was the early version, which was really bulky, but now we are able to find a really small vacuum motor that can support the operations. And yeah, so diving into more, right? We have those 4-degree freedom we talk about, right? X, Y, Z plus a rotation so that we can pick the fruit. So it's very kind of simple in design. And also we have a vacuum system. This was from last year. So we are using one vacuum, okay, to support 2 arms. And so we have to coordinate the 2 arms, and which also kind of slow down the process. So this year, this version, we're going to have separate vacuum motors, because previously we only have those kind of bulky ones. We do not have space to use 2 separate ones. But now we are lucky that we find a really compact vacuum motors. So we're going to use 2. Well, last season, right, we are doing some coordination, which I will show as well some of the algorithm we use to coordinate the vacuum and 2 arms to harvest the fruits. And also the robotic platform can also go up and down and in and out to accommodate different canopy structure. So now I'm gonna quickly go through some software part, right? So the software part starts with a perception algorithm. So perception starts with the detection algorithm. So detection, this is some interesting aspect. So we first thought, right, when the project first started, we thought that one of the big challenges is to have a comprehensive data set. And then we need to find and get a good architecture for this apple picking detection system so that it can work really well for this application. So we collect a lot of data, thousands of images across different orchards. We actually also collected data for some other tree fruits, right, like citrus and avocado. And then we trained the models on top of that. And we achieved state-of-the-art performance. We had a paper called occluder-occludee network that achieved the state-of-the-art performance was like a 93%. Okay, we were quite happy and it works quite well. But all of a sudden, like the foundation models came out. Okay, so we tried quickly a foundation model, which is called the grounding dino. And this foundation model, we used the thousands of images to train to achieve 93 point something performance. But after we applied the foundation model, we only used like a few hundreds of images to fine tune the foundation model. We actually achieve better performance. So yeah, that's something that's really kind of blow our mind. And so the models are really powerful and the generalization is very good. We can also give some prompt saying, okay, if we want the apples left, right, not occluded by branches, things like that. We can also incorporate some text prompt so that we can use for planning control. So I think overall, the fruit detection works very well. Even though there are occlusions by the leaves or branches, we're able to detect the fruits without a problem. So the next part, right? So here I'm showing is basically a sequential approach. We do detection, then we do localization, right? You have bounding boxes of the fruits, and then we do localization. So localization is actually quite challenging for this application. So the reason for that is, first of all, this is outdoor, right? So some of the cameras that work really well indoor, for example, the RealSense, it just doesn't work outdoors, okay? And also it's a very complicated background, right? You have multi-layer occlusions and challenging lighting conditions, and also we require high precision, right? We want to have millimeter level accuracy. And so that's why this is a very challenging part, and we spend a lot of time on that. We actually co-developed a 3D camera with a manufacturer that works really well for this application. That we try so many cameras, and that camera is the only one that works for our application. And based on that, we kind of work together to co-develop a 3D camera that works well. And then we developed the algorithm that basically we do segmentation, extract the point cloud of the apple with occlusions, and then we have algorithms to efficiently find the localization of the fruits. So then with all the fruits kind of detected and localized, and then we're gonna, because we have multiple arms, right? We will do the allocation, right? Which arm to pick which apples. So through this optimization allocation compared to the baseline nearest first, actually we can save more than 15% of the travel distance and the operation time. And then, as I mentioned, we need to coordinate the two arms to use the vacuum system from last season, right? Because we share one central vacuum system, and it's not allowed to basically the two arms using the same vacuum system at the same time. Otherwise, both arms won't have sufficient vacuum to suck fruit. So we developed some state machine temporal logic to coordinate the two arms. And then low-level control. So because the simplicity of our robotic design, so this is only 4-degree freedom system, and then we developed a Lyapunov function-based nonlinear controller, and it can achieve really kind of high throughput and also guaranteed the convergence and really high precision based on that. So yeah, those are some details I don't want to go through. And then each year we went out to commercial orchards to test. This is a very important part if you really want to have a system that's working, right, for real time, for the real world systems, not just developing things in lab. So it's important that you go to the commercial orchards. So directly test a robot, engage with growers, get their feedback, and then you go back and do the hard work and improve and come back next season. So this is this 2-arm module, okay, from last season. This was vertical lines, as you can see, right? This is kind of the commercial orchard condition. This was in Washington and Michigan. And let me show you some of the performance. Now I'll play a demo video, which will summarize what I showed, and then give some visuals about the system. So last year, we were able to achieve a success rate of 80%. So success rate here is not the picking rate yet, okay? Success rate is when we have 100 attempts, right? How many of the attempts will end up picking a fruit? So we're able to achieve the 80% and the 75% for 2 different orchards. So a lot of failures last year was actually due to the insufficient vacuum. So that vacuum had some issues with the overheating, and the vacuum power was not sufficient. So that caused a lot of misses. So this year we should have a much better success rate. And we look at the picking rate. So because we only have a 2-arm module, right? So this is only covers a section of the fruit instead of the whole orchard. So we didn't do a comprehensive analysis of the picking rate, meaning that how many of the fruits available will be picked. But based on our visual inspection, I think, yeah, it was around 70%. And also, we have the stem. Stem is also important thing to note, right? We want the stem from the fruits because with the stem, the apples will kind of stay fresh for longer, but also we need to kind of cut the stems. So we're working on the mechanism to cut the stems, but we want the stems to stay. That can help preserve the apples. So this is some percentage of the stem data. And also we look at the bruising. The bruising is really a key strength. So our bruising rate is really low. I think it's about 2% of bruising in the end. So let me play a quick demo video of the system. This is our 2-arm module, the platform. So we start with the detection and localization. So yeah, you can see a lot of bounding boxes. Those are the detection results. And within each of the bounding box, we do segmentation, and then we extract the point cloud, and then we do localization. And we can also extract the tree structure, which is important for pruning, which I will touch on that briefly. And this is our modular hardware design. So it's quite simple but effective, and we use a vacuum. So we did a vacuum design and soft-suction design. So those are a few clips of the robot working in the real ultra conditions. As you can see that the robot can work across different ultra conditions day and night, okay? So the robot works really well at night because it's actually easier as we just use artificial lighting, okay, to control. And this is the fruit handling system. After we harvest the fruits, we're gonna need to make sure that fruit will go to the bin without damaging the fruits. Yeah, that shows how the system works, the real prototype. So now I'm going to talk about maybe something more scientifically interesting. Okay, this is like a backbone and what works well in practice, right? The system really works well in practice. But on top of that, I'm going to talk about a few extensions, things we work on. So one is we call selective harvesting. So selective harvesting, basically the idea is that we want to make sure that the fruits, right, be harvested are ready, right? They are ripe, right, and the appropriate size. And also, we need to deal with the obstacles because there's some fruits that behind the obstacles. So yeah, this is what we call selective harvesting. Some of the fruits, if it's just hiding behind the branches and make it really hard to harvest, and if we harvest, it will kind of bruise the fruit, then we better not to harvest. And we can leave those for the human pickers to pick. So yeah, we then developed, we basically curated a data set for, we call this a ripeness data set for the fruits that will cover the color and size, right, of the fruits. And then we use that information to determine whether the fruit is ready to be picked. And we're able to achieve 86% classification results and still improving. And then we are also working on the effective methods that the robot actually can use, even though it has limited degree of freedom, right? Actually can kind of navigate through the canopy and pick the fruit. So we're also developing some fast marching based methods to do kind of navigation within more complicated backgrounds. Okay. So the next thing we're doing is a hybrid visual surveying system for apple harvesting. Let me tell a little bit about this background, right? So right now, as you can see, we are using one central central camera to do the perception. The advantage for that is that we have a global view and we can coordinate two arms. But as you can see from the charts, right? So those kind of 3D cameras, the accuracy will be better if you do close proximity, right? So if it's closer, then the accuracy is typically better. So then our idea is that in order to make this really robust, and it will be beneficial for us, right, to have an auxiliary camera that we call eye in hand, right, that can go with the arm, that it can see the fruit, and then we have a better localization results, and then we can have more robustness for the picking process, right? That's kind of the motivation that we can have a hybrid visual system to do the work. So yeah, this is the kind of idea, right? This is we call this hybrid visual surveying idea. So the whole process now has two phases. One is approaching phase, right? So we're gonna go to use the global camera to go to the target fruits, right? The rough estimate of XYZ. And when it's going to if the robot is able to pick the fruit, then that's good. Somehow, if the robot is not able to pick the fruit, and then we go to the phase 2, which is use a visual surveying from the camera we have. right? That the camera on top of the tube. So that's the idea that we're trying to kind of fuse those two cameras and to do this hybrid video serving. So the next part is the video serving, right? First phase is similar as what we have before. And second phase is this video serving idea that we're gonna use the real-time feedback from the camera on the tube, okay, to do the video serving to approach the fruit. So one challenge of this video serving approach is that, as you can see that, right, the arm is attached on top of the fruit and on top of the tube. And one challenge you can happen is that if you see the fruit, right, you see the fruit at this moment, and then if you start the video serving, you may lose the sight, okay? You may lose the sight of the fruit during the process. So it's important that we want to do video serving, but we do not want to lose the sight of the fruit. So we want to make sure that during the video serving process, we can see the fruit all the time. So basically, long story short, right, we developed this video serving, right, using the real-time feedback from the camera, but at the same time, we added constraints. So we use the control barrier function to make sure that the target fruit will always be in the sight, so we can pick the fruit robustly. So this is a kind of, so we basically artificially add arrows to the camera, right, localization. So you will always miss in the beginning. And then the second phase, we're using the video serving approach to pick the fruits. So we artificially add some arrows to that. Okay, that's that part. And then I'm also going to talk about some of the soft robot approach. So in my group, we had a few projects with NSF on the soft robot, and we also give it a try to see how the soft robot can be incorporated. So the idea is that in theory, right? So the soft robot has infinite dimension for the movement, right? Infinite degree of freedom, and then can navigate through complicated ultra environments. And also it's compliant. It won't damage the tree. It won't damage the fruit. And also it will be friendly when the human workers are in the scene. So that's kind of a lot of theoretical benefits. But practically, right, there's still gap to go. But yeah, we did some initial trying with the soft robot, right? So, and specifically, we fabricated a soft robot and we developed something called a direct data-driven control design. So the idea is that soft robot has a lot of benefits, as I mentioned, but controlling the soft robot can be challenging because of the modeling process, right? Some people are using the piecewise constant curvature model, okay, to use that model as to do control designs, which will show that many times it's just not a very good model, especially when you have bigger maneuvers. So, and it also requires a lot of domain expertise. So the idea of using data-driven model, data-enabled predictive control, which I'm going to show here, is that it's really just it does not require explicit model of the system. Okay, so all we need to do is to collect input and output data, right? So this is the soft robot arm we fabricated, and then we will give the inputs, which are the kind of pressure of the chambers, and then we're going to collect the output, which are the movements of the markers at the end. So you can see that this is data collection process, and then this is a data-driven, data-enabled predictive control, or deep C approach. Basically, it's based on what we call fundamental lemma or behavior system theory, that it will basically process the input data and output data in a systematic way into something we call Hankel matrix. And then with this Hankel matrix and fundamental lemma basically says that, right? So this is initially starts with a linear system. So if you have a linear system, this theory basically says if your data library, right, this input and output data you put together into a Hankel matrix, if your data library is sufficiently large, and then the idea is that you have so many columns, right, of your trajectories, And then the combination of your combined U initial, which is like a buffer, right? You stored for the input and output, and the future predicted U and Y together, right? Will be a linear combination of those trajectories in your library. So that's very simple idea in the linear LTI system. And in order to make this work for a nonlinear system, actually, all we need to do is to add some auxiliary variables and also we call slack variables in the system and also in the cost function. And actually, this method works quite well. And then we can basically do MPC-like control design, right? Instead of using the explicit model, okay? And what we can do is we just use this fundamental lemma-based model to represent the dynamic system. So, and we're going to compile this with the MPC that we have a simplified model. So that's the key difference in this. And then this is our setup for the controls. And there's some results. As you can see that with the data-driven, data-enabled predict control, by just collecting input and output data, and the robot will be able to kind of track different trajectories very well. And if you look at the numeric comparison, the data-driven predictive control actually performs better than the model-based control benchmark, as well as the MPC based on the piecewise constant curvature model. Okay, it's quite easy to implement and it works quite well. Okay, so I'm gonna talk a little bit about the in-field sorting part. So this is the background, right? So let me tell a little bit how the fruit industry works. So when the growers pick all the fruits, right? And then they put it into bins, and then the bins will be directly sent to, they call storage room, okay? The storage room really use something called control atmosphere. So they kind of extract all the oxygen and then put a lot of nitrogen. So the storage room can actually keep the fruits fresh for almost 18 months, okay? Up to 18 months. So then when they receive orders, right? So the packing house receive orders from Walmart, from Costco, and then they will go to the storage room. And then they have this packing line. So the packing line basically, what the packing line does is they will sort the fruit into those fruit that can go to fresh market, and those fruits, they cannot go to fresh market. They can only be used as processing, okay? But in that process, right, you can see that a lot of those fruits that won't be able to go to fresh market, they still need to pay the storage fees and packing fees, okay? So the growers talk to us saying, because you guys are picking the fruits using robots anyways, can you guys do an in-field sorting? We call this in-field sorting. So the idea is that after we pick the fruits in the field, we can directly run a sorting line to classify the fruits that can go to fresh market and the fruits cannot go to fresh market. So what we do is we based on the size, right? Because the size needs to be appropriate. And we look at the color distribution because some of the fruits in the front, you see that the color is pretty good. But once you pick those fruits, and then you see that the back at the color distribution is not very good. So you cannot go to fresh market. You cannot produce high value. And also whether there's any like marks, right? Any damages, then you cannot go to fresh market. So this project is led by Dr. Eugene Lu, but part of the USDA project for this in-field sorting. Yeah, as you can see, we developed this architecture that we can use the size, color, and also the curvature, and whether there's any damages of the fruit to determine whether the fruits actually can go to fresh market or not. So here's I think this video to show how it works. As you can see that it goes pretty fast. It can go like 2 to 3 fruits per second per lane. And here are some of the results, right? So those are the results based on the difference running speed. So if we go like 1 apple per lane per second, then the accuracy can go like 97%. If we increase the speed, right, the accuracy kind of decreases a little bit. But overall, I think it's still very good, the performance, and can do a very good kind of pre-screening of the fruits that can go to fresh market versus has to go to the processing for the growers. Okay, so yeah, I think I'm going quite fast. So I have a few more slides, right, to show what I'm working on right now. So this is a platform we put together. So what I showed you earlier is just we call this two-arm module, right? So this is a two-arm module, as you can see here. Those are what we have already demonstrated. So now we're actually putting four those two-arm modules together onto the system. Okay, this is what we're working right now. So then this complete system will have 8 arms, right? We'll harvest the fruits on the 2 sides of the orchard, right? And we also have a cockpit for now, right? Because it's not fully autonomous yet. We have some LiDAR and camera sensors that the vehicle basically can go near the center of the lane, right? Won't hit the trees. But we do not have the autonomous kind of driving. If you give a reference trajectory, we'll just harvest that way. That's not our focus for this year. But so we still have a cockpit. So we can have operator to drive the vehicle after one lane is finished, right? And then make a turn, and then you can keep going. So this is the in-field sorting system I just showed. So it will be integrated onto the platform, and then we'll have fruits, and then we'll be able to process the fruit. And we have 2 different bins. One bin is go to fresh market, right? Those fruits that can go to fresh market. And then we have a cold bin, means that the fruits will only be used for processing. So we have 2 bins, and we have a lifting function. So once one bin is full, then we can unload the bin, and then we can pick up a new bin. So the process continues. Okay, so this is something we're working on. So we want to finish this by the end of June or latest early July. And the harvest season typically starts in maybe mid to late August, right? So we want to have everything ready by then, so that we can deploy the robots in the commercial orchards this year. So this is something we're working on right now. And another thing, we have started the collaboration with Meta is the pruning, right? So the ultimate goal of this robotic system, as you can see, the robotic system, we have the perception module, we have the manipulators, and we want to use the shared hardware, right? To not only just for harvesting fruits, but we also want to do pruning. So pruning is the second largest kind of labor cost for growers, right? And pruning is very important, because if you do not prune the branches, then what you will have is a lot of small fruits. So they cannot go to fresh market. The value will be very low. But if you over prune, and what will happen is that you have a small number of really large fruits, right? Which also not very good. So actually pruning requires a lot of expertise. And sometimes there's no kind of fixed rule how do you prune, but the pruning experts knows how to prune, okay? But right, there's no fixed rule that everybody is following, but they know how to prune. So what we're doing with Meta is that, so Meta has something called AR glasses. So what we are doing right now is a non-intrusive way to collect data, right? So we can have the worker to wear the glass, right? To have some audio instruction. So what we want them to do is first kind of capture this tree in different angles so that we can do 3D Gaussian splatting, and then we can reconstruct the tree. And then we can have this tree structure in the simulated environment, right? This is the real to sim part. So we can kind of use this really nice non-intrusive way to collect data and put those into a simulation environment. And then within this simulation environment, we have a lot of trees, and then we can apply the physical kind of properties to the trees, right? Many people using the springs to represent the tree physical properties. And then we're going to develop decision-making models using VLM or VLA. This is more appropriate because you can see in our apple harvesting approach, it's more sequential, right? We use AI, but it's mainly for perception, not for the decision making, because apples actually, I think the harvesting works quite well for harvesting. But pruning, again, there's no fixed rule, because for picking, we know, okay, here's the target fruit. The goal is to pick that. But we're given a tree structure, really a lot of factors, a lot of knowledge is needed, right, to make that decision, which kind of branch to cut. Okay, so we're developing VLA model such that we can give the decisions. So this whole thing, right, can be used to train the pruner, right, when they are really kind of new, but ultimately, right, so we want to be able to make this autonomous. But in the interim, this system can do is to provide a training to the new workers, right? When they first come, it's also, again, seasonal labor. They may never did pruning in the past. And then we're going to send them to the US to do the work, and a lot of training due to the language barrier, right? All kinds of things that make this actually quite difficult for them to, so it's always suboptimal way instructions for them to cut. But with all this, we can provide more tailored instructions to the workers, so to train them, but eventually, ultimately, right, we can make all the things kind of fully autonomous. Okay. Yeah, I think, yeah, that's pretty much all I have. Yeah, some acknowledgements to the students, collaborators from USA, Dr. Renfu Lu, and also the unwavering support from the growers, the orchards from Michigan and Washington. That's pretty much it. Yeah, thank you very much.
Thank you for keeping the printing short so our students can enjoy the spring break. But before that, any questions, please?
Well, one of the earlier slides, you have successful rate of two different orchards.
Yeah.
One is Jeff's, and one is I think Keith.
Yeah.
80%, 75%.
Yeah.
There is a possibility that success rate also depends on how it's pruned, or how if it's depending not just machine but also how the apple is actually presented for the machine.
Yes, yes. So the at this stage is still highly dependent on the orchard conditions, right? If the orchard is not managed well, meaning that a lot of occlusions by leaves and branches. So again, the detection won't be a problem. So we can still detect the fruit even there's only a small portion of the fruit is visible. But the challenge is the detection, because we need to use the pixels, right, from the apples, and the 3D cameras we use, inevitably they have a lot of noises near the boundary. So we do some erosion, right? We do not use the boundary. But if the area of the visible apple pixels, the number is so small, then it's just noise. It's not usable. So the localization can be a big problem if we have heavier occlusions. So yeah, so the management of the orchard is still very important. But our target is to work on above average orchards, not like ideal orchards, right? So, and we want the system to be able to do the harvesting with a moderate occlusion, meaning that, let's say 50% of the fruit, the fruit is visible. So then we're gonna go pick those fruits. But if it's more than 80%, we probably just leave this for humans to pick. Otherwise, if we go attempt, and many times probably just a miss, so it will affect the efficiency. Yeah.
I had a question from by the good talk. I think they enjoyed the project. I had a question about the safety engineering of this. Like, let's say there's a buzz nest in the tree, right? You don't want to like go and like affect any of the animals living in the ecosystem. If this is going to be implemented, how do you plan to like address any safety considerations about the environment and the like the ecological system? That's it.
We have the obstacle avoidance already in the new platform I just showed. Yeah, we have that. So safety, that safety, right? We have already considered. So basically, if there are, yeah, we have this actually the sensors and algorithms to detect the humans, detect the boxes, the bins. And so we want to kind of hurt people and hurt the damage the boxes. But the disturbance to animals, yeah, I actually, yeah, it's not our focus for now. But I think I don't know what kind of animals may appear in the orchard. But during the harvesting time, maybe not a big problem, a concern, at least to the growers. Yeah, yeah. Yes.
On the data-driven mold predictive control for the soft robotic manipulator, how does it perform when you add the load of the apple at the end effector?
Great question. We have another paper actually working on that. So we had a paper we call this velocity-based deep sea. So basically we derived the velocity-based form. So that will work when you have a constant load, right? So basically we come up with a way that if you have a constant load, actually you will be able to take care of that. So there's we call it velocity-based deep sea. Yeah, we had a publication on that as well. So as long as it's a constant load, we'll be able to take care of that. And the performance will just as what we have. Yes.
Have you considered, like, I mean, sort of thinking about the aspect of active planning to, go to a different like angle to get a better view of the apples? I mean, visual servoing does this at sort of a local level, but in a more sort of global sense.
So I think to answer your question, I think there are two aspects. Practically, I think we probably won't go that path because the speed is really a key. If let's say it takes more than 10 seconds or even like 5 seconds to pick one fruit with the two-arm, then the growers will think it's too slow. So practically, they want the system to be able to harvest fruits fast. Efficiency is very important. Scientifically, those are very interesting questions, and the visual servoing or the active perception that you go around the fruit at different angles, then you can better do even like a 3D kind of modeling orientation, things like that. Those are possible, and we also explored in the past. But practically, yeah, this is very hard to implement because you have to, like, for one fruit, right, you have to go to different directions that will significantly slow down the process. So I think, yeah, scientifically interesting, but practically, this will be kind of hard to be incorporated. Yeah.
Very good talk to like combine the credits. I'm curious about what is the most like surprising feedback from the orchards when you are deploying the.
Oh yeah, good question. So yeah, we had a NSF soft robot project from the national. There's a kind of a national robotics initiative project. So our first version we actually bring to the orchard we call this hybrid. So one segment is basically rigid, and then we attach a small segment of the soft robot, right? So that has the potential benefit that it can go pretty fast for the rigid part, and then you also have some degree for them to navigate. The growers don't like it, right? They just want speed, and they said, I do not expect you to pick like all the fruits, right? As long as you can pick 70% of fruits, they will be super happy. So I think that's one important part is if you do not talk to the growers, and as a researcher, many times you want to see, okay, how can I design a system? How can I design my mechanism that I can pick like 100% of fruits? But that's not a way to go if your goal is to serve the growers, right? So it's a better idea that you engage with your customers early and see what their real needs is instead of just developing in the lab. I think that's a very important lesson we learned when we first show the prototype. Yeah, they don't like it. Yeah.
Thank you.
Yeah.
So like adding on to like that, so you can use like a second robot or like a drone to like have a better view around the tree, like if you're missing enough around before you send out the main robot to like collect it. So you can have like 2 maps, and then you can like then you can take the information from this one that okay, maybe the robot that's picking the fruit missed the apples that were seen by the drone, maybe behind the leaf, some place. So you get like better.
Yeah. I mean, all those things are really kind of good directions to explore. And we try some of those things, right? Basically, you have a collaboration between two arms. So one arm basically move the branch to the side so that the other arm can approach the fruit better. Yeah, we did some study on that. Yeah, that's durable. But again, practically probably not a good way to do, right? If you cannot pick the fruit, just pass, right? And we want to kind of engage with the growers next season, do better pruning, right? Do not have those kind of branch stick out. So that's a better way to address the problem instead of making the system too complicated. Yeah.
So going back to interesting design of the arm, the custom design arm. So compared to, for example, off-the-shelf arm, when you design that, what is the decisive factor that you make this configuration of vacuum and pull rather than, for example, snipping or other forms of harvesting?
Yeah, we tried a lot of mechanism to pick the fruit, right? Right now we're using vacuum. We tried a soft gripper. We tried the claw design. So in the end, we think that the vacuum is the best for the following reasons. First of all, if you look at the claw or you look at the softer fingers, right? It typically is electric driven, so you have to kind of place the motors. So make the whole end effector really heavy. And that caused a lot of slow down the system, and also the durability can be a problem. And the vacuum system, the beauty of the vacuum system is you see like end effect is so light, right? It's just a soft cup, and then you can move around, and also we can do really good control of the vacuum system. And it's also really cost effective. So all things considered, we think that a vacuum is the best way to go for the fruit picking. And going back to your question about the degree of freedom we may need, right? So we have the 3 degree of freedom for XYZ, and then we have rotation. So basically the idea is that this rotation can help detach the fruit. But the idea is after we talk to the growers, actually they have mixed feedback about this rotation part. So for some of the varieties, they said it's better just pull so that it could better retain the stems actually, and then less damage to the tree. But some of the varieties, it's good to twist. So I think we need to have that functionality, and then later we can kind of try different picking patterns, right? For example, you can go back a little bit, then twist, and then pull. Maybe it's better. So yeah, there are more explorations to do, but yeah, we have those 4 degrees of freedom. We think it's necessary and works quite well so far. Yeah.
I think we have a question from Zoom.
Probably after that question. Go ahead.
I'm just wondering, have you tried your system in different weather conditions? For example, like in rainy day or like windy day, like today. If the wind make the apple shake, will it impact the detection? And how does it perform?
Good question. We haven't tried in raining days because the system, I think it is still prototype. Haven't made the system to be like IP67, that kind of protection level. But yeah, we did try in the windy days. We have pretty good results in the windy days because our algorithm is not just detection, it's actually tracking. So the fruits are actually tracked. So slight movement is fine as long as not too big shift. Yeah, some small vibrations is fine. Yeah.
And Professor Shi might have a question online.
Okay. Yeah, thank you. Zhaojian, thank you very much. Visiting Purdue. I'm sorry I didn't, present on site. Fantastic talk. So I have a brief question and want to seek your suggestion. Kind of a similar question previously one student asked, why not consider other form factor? Why, prefer the suction cup? I get some of the information, for example, maybe if we're using gripper, you have more additional inertia, like the payload from the motors. So that will create a kind of instability. I'm just wondering if we purely focus on suction cup, will it create some potential limitations? For example, we may not have feedback from the suction cup, and every single time when you do the harvesting, can we ensure this is stably grasped? It won't fall, and we can detach from the stern. And also, if we apply significant large amount of a vacuum, potentially it will either potentially damage the fruit. So I just wondering if there are any limitations with the suction cup, and potentially will tactile sensors play a role here? Because I work on tactile sensors, I try to see how this could be relevant. Yeah, thanks.
Yeah, thank you. Yeah, great question. Yeah, tactile sensing, actually, yeah, you know Zhaojian, and actually Zhaojian and I had got a project actually working on the tactile sensing based harvesting. So the idea is that on the soft suction cup, we are embedding the tactile sensing capabilities. So we know what we touched, right? So for example, when you touch a branch versus you touch a fruit, it's different. So actually are working on that as well. That's to your question. I think tactile sensing can be helpful in those contexts. And the limitation wise, so the benefits of the vacuum is that we will have sufficient airflow rate. So even though the localization is a little bit off, right? For example, by 1.5 centimeters, and due to the big airflow rate, we'll still be able to kind of attract the fruit. But the challenge was that the power consumption from last season, right? You can see really kind of a big bulky kind of vacuum. We bought this from like off the shelf. It's industry kind of vacuum system, and actually the power is really heavy. I think it's 1.8 kilowatt, right? If you think that we're gonna have 8 arms, then that's not possible. So that was a big concern. But yeah, we were able to find really low power requirements, only around 800 watts, but we can also control the power. So the previous one is AC cannot control the power, but now we are using a DC vacuum motor. We can control the power. As you can see that when we need to attract the fruit, detach the fruit, then we should use the most of power, right? But after that, we can actually slow down the motor, and then the power actually on average will be quite manageable. So yeah, I think the previous biggest concern we had for the vacuum-based approach was the power consumption and also the space. But now we find a good solution to address that concern. Yeah.
Well, wonderful. Thank you. Thank you so much, Zhaojian. Wonderful. Thanks. Yeah.
Thank you.
All right. That would conclude today's talk. Let's thank our speaker one more time. Thank you, everyone. We go with Professor Lee, and also we're gonna take 2-week break. So next week is gonna be spring break. A week after spring break, it's gonna be actually Purdue Robotics Day. So we will not have our icon seminar. Instead, we'll have the Purdue Robotics Day in PMU. You must have already received the email. But if you don't have any more information, feel free to ask us. And then we'll reconvene after 2 weeks. Enjoy the spring break. Thank you.